Okay, our next topic in our cartography review is map projections, which is our method of taking our three-dimensional Earth and flattening it out onto a flat map. One way to sort of picture this in your head, this is not really how it's done, but you can imagine taking this globe, placing a surface around it, and we put a light bulb in the middle of the globe, and it projects what's on the globe onto that surface, and then we can unroll the surface onto a flat map. So map projections are actually mathematical equations that are converting our three-dimensional Earth into a two-dimensional map. In that process, reality gets distorted. So it's impossible for us to take our 3D globe and render it on a flat map without having some kind of distortion. So our goal with projections is to try to minimize the distortion as much as possible and to make that minimization of distortion fit the purpose of the map that we're working with. So we have three options for the developable surface. We can project the Earth's surface onto a plane, we can project it onto a cylinder, or we can project it onto a cone. The distortion of our mapped area is minimized, it's the least at the point where the developable surface makes contact with the globe. And for a plane, if you imagine here's your plane and here is your Earth, it's gonna, if this is my fist were an actual sphere, or here, let's take this, and we put our plane against it, the point of contact, it's a point. And so the least amount of distortion is at that point. If we wrap a cylinder around this, it's going to have a line that is the point of contact, and that's called a standard line. And if it's a cone, it's going to have a line of contact. And that's where you have the least distortion. As far as you move away from that point of contact or that line of contact, distortion increases. So if we have planar projections, we can intersect our Earth with the plane at a point, or we could slice our planar projection through the globe and make what's called a secant planar projection, which has minimal distortion around. There's a circle of contact there, and it's reduced distortion in that area. We can take a conic projection, and in this case, our line of tangency would be along a parallel, kind of in the mid-latitudes in the northern hemisphere. Conic projections are often used to project maps of North America because the line of tangency is a parallel in the mid-latitudes, which works really well across North America. A secant kind of projection actually intersects the globe and again makes a region of minimized distortion. Cylindrical projections can be tangent to the globe along a meridian, or you could turn it so that it's along a parallel. A transverse cylindrical projection is one that we're going to talk about quite a bit, because this is the projection that's used to create the map for the UTM grid system. So in this case, the cylinder is placed around the globe this way so that our line of tangency goes along a parallel. And so what happens is you end up with a long skinny strip that is projected or mapped with minimized distortion, which this is the foundation again for the UTM grid system. So you have this skinny strip that is projected with minimum distortion. So just to give you an idea of how different an area looks with the distortion with different projections, the green is unprojected latitude and longitude. So you can see this top boundary is pretty flat. Maine gets kind of stretched out here, and Florida is sort of pulled in. A Lambert conformal conic is a conic projection. The Mercator projection is a cylindrical projection, so you can see how different the projections get. If the point of tangency is here at the center, the further we go, the more distorted they are. And looking at all of North America, comparing an Albers equal area and a Lambert conformal conic. So the equal area is conserving area, the conformal conic is conserving shape, and you can see as we get up into Alaska and Greenland, they look quite different. So the green one, the shape looks right, but the size is incorrect and is distorted. And the maroon one, the area is preserved, but the shape is distorted. And then if you get down here into the Southern Central America and Northern South America, you can see big changes down there too. So if you have to choose a projection for a map, you want to think about the size of the area you're mapping, the latitude, and the shape. So you want to try to get your point or line or area of tangency, or where the secant intersection occurs, to line up with as much of the area that you're mapping as possible to minimize your distortion.